So hi guys, I am Parampreet Singh, and as we are like doing MLP sessions this term, today we will be having our ninth session. Okay, and this ninth session, as I said, I'll upload all the recordings of the session in my YouTube channel, so you can subscribe to it for the today's session recording and the upcoming session recording also. Okay. So in today's session, we will be mainly doing the linear regression. In last session number 8, we did the linear regression, but we did the complete basically working how it works in detail. Okay. Uh, so today we won't be we won't focus on the details of like how linear regression works and all. Um, of course, I will give you a recap, but we will mainly cover the concepts which are in the week 4 of MLP, which is the linear regression and its variants, like whether it's using normal equation, gradient descent, or the regularizations like ridge or lasso. Okay, also some other parameters as well which you use. Yeah, start. So this is the notebook which I have created earlier also. I did some modifications for like today's session. Also, I did some more plots. So, okay, let's start. Okay, first, how many of you know what is linear regression? Just like the definition or anything. Like, how many of you heard about linear regression? You can even speak up, guys. Okay, and how many of you know about the how many of you know the implementation of linear regression?
No, that I don't know.
Okay,
No.
and how many of you know about cost function?
Yeah, cost function is that error, right?
Right, and what
Yeah.
about the gradient descent?
Yeah, that also have a idea.
Okay,
A bit of idea.
okay. Palavira, you were in the previous session, of course. So yes. Okay, I'll give you all just okay. I'll do the complete linear regression today. Okay, because today's topic is that. So uh, what a linear regression is, it's like as the name suggests, it's a regression model. Okay, regression, by regression we means like we are predicting a continuous variable. Okay,
Hmm.
so continuous variables means we have two types of data generally, like either discrete values or continuous values. So uh, continuous values like are in some specific range, but they like we cannot count them as in like actual. Okay, so linear this is the regression thing. And in regression, like we will be today doing linear regression. And linear regression, okay, sorry for the handwriting. Okay, and in linear regression, it is a supervised learning algorithm. Okay, so there are various kinds of like techniques to do the machine learning, basically to train the model and all. Supervised learning, unsupervised learning, self-supervised, reinforcement. Okay, and uh, like in supervised learning, we have various kinds of, specifically in regression, we have various kinds of techniques like linear regression or tree-based models and support vector machines or some other like naive Bayes and all, like different kinds of algorithms we have. Okay, but today we will be mainly focusing on linear regression, how it works, its cost function and gradient descent. Okay, also it's, you can say, uh, the regularizations also, like it's a, okay, इनका ये kind of a plus version for the linear regression, which are ridge regression and lasso regression. Okay, these are the regularization techniques for the linear regression. So the base is this. And also just want to like give you basic this is just a basic knowledge based on the linear regression only. we have a model called logistic regression. Okay, logistic regression, it like the name is logistic regression, but it is a classification model. Okay, it is used for like doing the classification stuff, whether it's a binary classification or multi-class classification. Okay, so let's start. uh,
What do you mean by continuous? Means you mean the data or features should be continuous
okay, by
in linear?
continuous I means okay, in discrete we have some specific amount of values, like we can count them. Let's suppose the age we can count, right? 18, 20, 24, something like that. But temperature and weight we cannot count, because we have temperature in floating point values, right? uh, like temperature can be anything, 24.6 or 24.8, something like that. So there can be like infinite values in a range, like in a specific range you can say. So that is that is the continuous variable. Okay.
No, my question was means the input data should be continuous for the regression.
No, input data shouldn't be. Input data should be just the input should be just a numbers. Okay. uh, it doesn't need to be like continuous or discrete. Okay. The equation which we have for linear regression, it basically do the stuff for us, gives us the result in a continuous variable. Okay, so let's start.
Okay.
Linear regression. So before the like linear regression, of course, आप सबने मैथ्स वन तो करा ही होगा. आई एम assuming मैथ्स वन एंड मैथ्स टू you have did. And like uh okay, let me just give you some intuition. So let's suppose we have a plot like this, and we are doing the house price prediction. In y we have the price, and in x we have the, let's suppose, say size. I'm just taking this a simple example because it is a very basic example, just like which everybody can understood easily. So we are like plotting the scatter plots, like here you can see we are plotting some points. Okay, so uh, these are all the points. Now let's say if we have some new house sample, and that sample is like the size of the house sample is here. Okay, you can say here. So based on this, if you like generally check, this dot is matching to this size, also this is also matching, but let's just ignore this for now. And if you see, this dot is mapping, like intercepting the y-axis here. Okay, so this we can say this is the price for this house size s. Okay, this is just a general, like you can say, mapping. But like we cannot do this for like different various house sizes, because we do not have like all the house sizes data like at the starting. So what we do is we basically create a line based on the data we have. Okay, so let's suppose this line I have created. Okay, or let me like do some better. Yeah, this is the line we have created. Now based on this line we will predict the house prices. How? Let's suppose the size is this. Okay, so wherever the size is intercepting this line, let's suppose here. Okay, and the same point, at the same point where the y-axis is intercepting, this will be the price of our house. Okay, so this is how like the working of linear regression is. This is just you can say an abstract overview. This is not the in-depth I'm like explaining you all right now. So this is a basic thing, and the main task in the linear regression is to find this perfect line. Like how? Let's suppose, okay, let me create a new one. Let's suppose we have the same data set. Okay, y here, x here, and I have some plots, some points here. Same I am like plotting here as well. Okay, same I am plotting here. uh, let's suppose the data is same on each of these plots. Okay, all the three plots. And now if I like plot this line or this line, or let's suppose this line, and let's say this is A, this is B, and this is C, which line would you think is the like best fit for the data? Like which line can give us the best results for the house size which we input here? A,
A.
A.
B, or C? Okay. Everybody is like agreeing with A, option A, or do you like you say B or C? If you have anything like you can speak up. It's not like it's not a lecture, guys. So A, give a thumbs up like if you
Yes.
are okay. Okay. So A, right. Uh, you all are like right. Obviously A, because it is kind of uh, go. It is the like same direction on which our data is spreaded. Okay. You can say it is like directly correlating with our data. Okay. And like in this A line also, let's suppose we have various okay, let me plot it in a new one. So we have this plot, this, and this. Now in A only, let's take only these much values. Okay, I'm trying to like plot the same one, and like normally like by looking at the data, you all said A, right? So here what if you see, like obviously the models cannot like just plot the data, visualize them, and do tell us which is the best fit line, right? They have to do some calculations. So what in linear regression we do is we calculate the difference between the predicted value and the actual value. Let's suppose the size we have provided here, which is S, okay, and by the line the price we are getting is something like here. Okay, I'm just writing it as a y hat for now. Okay, and but the actual house sorry, actual price for that house is something here, which you can see here. Okay, so this difference which is like between the y and y hat, this is the error, you can say. Okay, and by like in linear regression we have to choose the like we have to make our line best fit to the data. By best fit what sorry, by best fit what I mean is we have to minimize the error. Like here if you see, this is closest to this, and the error here we have like this. Okay, uh, like this and this. Similarly here also we have some error like this, but here you can see we have some huge error here. So by like calculating these errors, the linear regression can tell where like which line is best fit by like looking whichever has the minimum error. Okay, this is also a general overview. uh, the main thing which we do is we have like we can start with any kind of line. Let's suppose we have started with this line, we have to translate this line in such a way that it goes into the best fit from there to here. Okay, so this is what we do in linear regression, and this what I told you here, this error,
So that, sorry,
yes, yes, yes.
just to confirm the lines that you have drawn to the um, from the various points to the
Mm-hmm.
line L, all these shorter lines that you have drawn, which you call as errors, they are
Yes.
perpendicular to the line L, correct?
Right. So, sorry, I
They are
forgot
all
to mention that these are perpendicular to these lines. Okay.
okay.
So this you can also say this is a kind of a mapping which we this is similar to a mapping which we do in PCA, but of course I'm not we don't do something like that. It's just like overview I am giving to you all. So this is like the error we have. Okay, these are all the perpendicular lines, of course. Now okay, before that, let me run this. Let me show you this in the okay. So here can you see this graph? Guys, can you all see this graph?
Yeah, yeah.
Yeah.
Yeah, it's
Uh,
visible.
this is the, like
Yes.
you can say, this green line is the best fit line. Okay. And these are some samples we have in blue dots. And the error in the blue dot as well as the green line is the red dashed line, which you can see here. Okay. Here I have plotted only for like 5 samples. If I set samples to, let's say, 10, and if I run it, now you can see the error in the difference between the actual scatter points, actual you can say actual price, and the price which is to be predicted by the this linear regression line. Okay, so this is the error. Okay, this is the graph which I forgot to add in the previous session. I hope this is clear to you all. Is this clear? Like,
Yeah, yeah.
can
Like,
you okay. So now let's get back to the linear regression. In linear regression, the formula we have is because we just have to plot a single line. With the formula we have is wx. Okay, let me write. We have is f of x with wx plus b. Now it is similar to the formula we have for a linear, like okay, to plot a linear equation, like uh, in maths one also, and in high school, like we create like when we are starting with the equations, we start with the one equation which is a linear equation in one variable, right? This is the formula for that, mx plus b. Am I right, guys?
Yeah.
This is the formula for linear equation in one variable,
Mm-hmm.
where m is the slope and b is the intercept, right? So this is the general notation which everybody follows, right? Most of the people follow. So the same equation we have here. Now you might be wondering, like, this is the same thing which we are like learning since school, and this is the same model, like this is the same in machine learning. Yes, this is the same, but the thing is, we have to optimize these values, the slope as well as the intercept. Now there are just some notations for the linear regression. Let me write it. If like I am writing m, so m is the number of samples or the number of rows I am like saying. Okay, n represents number of features we have. Okay, then I, for I like we represent ith row. Like if I say, let's suppose x of, and I as in superscript. Okay, if I say x10, so I am representing 10th row of my dataset x. Okay, and j basically represent jth column. Okay, column or the feature. And then we have some other also, x for the data which we have, data with all the features, y target variable. Okay, these are some of the basic notations, and then we have one more notation which is y hat. It is like similar to y, but hat, this y hat represents the predicted data which we have. Okay, so predicted values you can say. So y hat represent this. Now like similar to this linear this equation of a uh, like this one variable equation, we have w and b here. What w and b are? W is the slope, which we also like say as weights. Okay, in machine learning terms, also like we also uh, call it as a coefficient. Okay, in scikit-learn you must have like seen, to check the coefficients we write coef underscore followed by a underscore, which basically represents the w. And we also have b, which is the intercept. Okay, and in machine learning terms we call it as a bias. Okay, so these are some of the basic notations. Are you all clear with these notations? Like if you have any doubt in these
Oh,
notations.
yes.
Okay, so these are the basic notations. Now like similar to the this line which we have here, like what does the in the linear equation line, if I plot it, okay, I should plot it in a new graph. If I have this graph, okay, and I have some points and I have a line, the slope, which is m or w, you can say, the slope what the slope does is it basically tells us how slant the line should be, right? If the slope is highly positive, like if the slope is highly positive, then our line will be more slant like this, right? If the slope is negative, then our line will start from a higher value, okay, and it go like it decreases as the value of the x increases, right? This is for the negative. And if we have the slope 0, the line is constant, right? Am I right, guys, about the slope, guys?
Yeah, yeah, yeah.
Okay. Next, I know like थोड़ा सा ज़्यादा हो रहा है, but just bear with me for a few minutes. If the concepts are clear, you all will be clear with a lot of machine learning algorithms, because linear regression is the base of many machine learning algorithms, as well as some optimization algorithms also. So then we have the bias, which is the intercept, okay, which is the b, which we have in the equation mx plus b or wx plus b. Okay, what bias do is it basically tells us where the line should intercept the y-axis. Okay, let's suppose we are starting from 0 and here it is 100. If the bias is 0, line will start from here. If the bias is let's say 10, the line will start from here. Okay, so this is what bias controls, like how much line should go, like where the line should intercept the y-axis. Okay, so this is the slope and bias. Now let me like show you the visualization of this so you will get the clear idea. So this, can you all see this graph?
Yes.
Yeah, it's visible.
Great. So
Yeah.
in this graph, okay, in this graph we have like some data points which are represented by this blue dot. Okay, and we have two lines here. Right now you can only see one line, which is the red line. This red line is the linear regression line which we have plotted. Okay, just to give you a simple like overview, basically what I am doing is I am using the make regression function from the scikit-learn library and creating a regression data set. Okay, and the we have like 1000 samples, which is the m, and 5 features, which is the n. Okay, and these are like first 5 samples of our x, and these are first 5 samples of our y, which is the target level. Okay, and then we are selecting only the first feature and doing the like creating the model and training the linear regression model, okay, on it. And we are doing the predictions on the actual training data set only. Okay, we are not creating any kind of validation data set, and that we are plotting it here. So if I run it again also, so this is the graph which you get, and this is just for the 500 samples I am using as of now. Okay, now these, as I said, these blue dots represent the samples and the red represents the regression line. There is also a green line which represents the regression line. Now this is okay, I'm not getting the slider here. Let me uh, reload it once. Session starting. Okay. Okay, I'm not getting the graph. I don't know why. Let me check. I'm restarting the session with like this Jupyter notebook. Okay. Okay. So now, yeah. Now I have this slider. So what I have done here is the W and B, which is W represent the weight, which is the slope, and B represent the bias. Okay. So by default, the W and
One sound is coming. Background
sorry,
noise. One noise is coming. Beep.
what you guys, can you like speak clearly, like
Beep.
more loudly?
Beep. Continuous beep is coming from outside.
Uh, okay, any sound is coming from my mic?
Yes, yes, yes.
Now is it
Now
clear?
it is. Now it is there.
Okay. So like W here we have as a weight, and B here we has the like as a bias. Okay, which is W is the slope and B is the intercept. And these are like some default values which I have said. These are the best values we can say for the linear regression model. Okay. And like if I play with this, like this is a slider for both of these parameters. If I like decrease the slope, you can see the red line will like the slope is in negative, so the red line is starting from a higher value and uh, going down as the value of x increases. Okay. And the green line which you can see, this is the best fit. So if I decrease the value of W more, the line will be more slant, but it is in the opposite direction. Okay. And if I increase the value of W, like let's say to 90, you can see the line is more slant, but it is now increasing as the value of x-axis, as the x-axis is increasing. Okay. So this is what, like how slope works. It's just to give you like the overview how slope works. Now if I like set it to the actual value which it was, let me run it again. Now for the B, which is the intercept, um, if I like decrease the B, you will see the red line will be like down, will be below on the now the red line is below the green line. Okay. If I increase the bias, the line will go up, okay, above the green line. So this is how bias, which is the intercept, works. Okay. So this is just a basic overview, and I will share this notebook with you all. What you can do is you can simply copy this notebook and run all these cells, and you can play it like you can tweak these variables by yourself and check how it is working. Okay. Till now, like the the basic is clear, like how slope and intercept uh, works. Okay. Now let's go further. So we were at, this is the graph which we have. Like right now I'm just taking, let's say, only 10 samples. Okay. So the line which I have plotted here. Now as I said, the difference between the actual point and the line predict and the point predicted by this linear regression line is the error we call. Okay. Like for some size s, if the value which is predicted by the line, we call it as y hat, and the actual value which you can say like which should be here, which is the y. Okay. And the difference between y and y hat is like y minus y hat is the error. Okay. We have various names, like we call it error, we call it loss, we call it cost. Okay. So these are the three things, like these are the three different names, we use them interchangeably. And like जब भी हमें error compute करना है, if we like check the error, so हर एक sample के लिए we'll get the different error, right? So let's suppose if the samples are 1000, so we will get 1000 different errors, but that doesn't tell us like how our line is, like हमारी line कितनी सही है and कितनी like how it is best or how it is worse. So what we do is we have some measures to like to check the error. We have some functions which basically measures the error in a certain way, and some of these are like mean absolute error, a mean square error, and there are others also. Okay, various kinds of error formulas. Of the main which we will be looking today is mean squared error. Okay, so as the name suggests, uh, mean squared error, what it does is it takes the error. Okay. You can just follow up the name, it takes the error and square it, okay, as the name suggests. And it basically sum up all the squares, like for the value for the sample 1, for the sample 2, and till all the samples. I can write it as like this, from I equals to 1 till m. And as the, like, it is a mean, so it divides by the total number of samples we have. So this is the formula for the mean square error, okay. And this is obviously, this gives us a scalar quantity, not an array of errors or something like that. So till now, is it clear, guys? uh, okay. uh, Guys, yeah. So should we like move ahead? If you have any
Yeah, yeah.
doubt or confusion, I can like explain it again.
So we can move ahead, I think.
Okay. So the error like which we plot here, the by looking at the function and the name also.
Paramji,
Yes, yes.
while finding the mean,
Mm-hmm.
suppose in case of there are some nan values.
Sorry,
So
can you repeat?
there are some nan values in an.
Okay.
So
We
we have to impute.
no. We exclude those nan values.
So suppose there are total 10,
Mm-hmm.
and out of 10 there are 3 nan.
Mm-hmm.
So we have to take addition of the remaining 7 and divide by 7, right?
Right, right.
Not
We,
divide by 10.
no. We
Okay.
exclude the nan values, and by default, whenever we do the modeling, we either impute those nan values with some value or we remove those rows, right? Right. We do not
Okay.
work the model. Basically, we cannot train the model with nan values. So, okay. Now, as the name suggests, this is a mean squared error, and like जो भी like this, if we plot the any square function, if we have, let's suppose if we plot the x square, it will be a parabola, right? Something like this. uh, the square function, if let's suppose it 0 is here, 2 is here, minus 2 is here, the values will be like same for the minus as well as plus, because it is basically squaring it. Similarly, for the mean square error, we have the same graph, okay, which is a square parabola, okay. You can also say it as a bowl, okay. So this is the mean square error graph. This is same as the which we have for the graph, same as the graph which we have for the like square functions, x square or any kind of, okay. Now like you might be wondering, why do we square the function? Why don't we like just take the direct value? So let's say if we have some data like this, okay, and let's suppose there are four values, y1 which is 10, y2 20, y3 let's say 30, and y4 which is 20, okay. And now let's say we also like plotted the line, and the values which we get from the line is something like this. For y1 we get same as the y hat 1, which is 10, and for the y2 we get the y hat 2, let's suppose, as 0, okay. And for y3, and this is just an example, okay, don't like consider it as a real. And for the y3, let's suppose we get something, let's say uh um okay, yeah. So for the y3, let's suppose we get similar like this, and for the y4, let's suppose we get the value as let's say minus, we can say, yeah, minus 20. And if we sum up normally, like if we do the difference, like y minus y hat, so here you can see the difference is, here the difference is 0, here the difference is 20, and here the difference is again 0. Now here the difference is, okay, let's suppose this y4 is 0, okay, and the y hat 4 is 20. This is just for the example, like to tell you why we cannot take the direct values, why do we square them. And here we get the like difference as minus 20. Now if we add them, we get the 0, but this 0 error doesn't tell us, like this error doesn't give us the better information. So that's why we do is we basically square those error. Now there is another way also. What we can do is we can take the absolute value, right? uh, Rather than squaring, we can take the absolute value. So if we take the absolute value, we will get something like this: 20 0 20, and the error will be 40, right? But the graph of the absolute value, अगर आप लोगों ने देखा होगा, if we plot the absolute function, so the graph will something like this. It will be a V, like a pointed graph, right? It will be of a V shaped graph. If I like also like just to confirm, absolute function graphs. So here you can see this, yeah, okay, yeah. So this graph which you can see here, this is the absolute value graph. Okay, this is the graph for the absolute function. This is like a V-shaped graph, and in the V-shaped like in the absolute graph, what we generally like, we cannot this function is not differentiable, right? This graph is not differentiable. Like we cannot compute the derivative at point 0, right? So that's why we don't take the mean absolute error as the base cost error. Okay, also like एक मैं थोड़ी सी चीज़ भूल गया था, this mean squared error, we जैसे हमारे पास like we have the fx as the function, okay, for the linear regression, this mean square error we call it as a j. Okay, so this is just a notation, and we call it as a error function, loss function, or a cost function. Okay, so this is the mean squared error. And if I show you here, like I have plotted the graph also, so you don't need to go through the code like actual code what I am doing here. Okay, okay, is the font size clear, by the way, for the notebook?
Yeah.
Okay, so this is like, this is the function for computing the mean square error. Okay, now I'm just running it, and what I'm doing is I am taking various okay, sorry, बस एक थोड़ा सा रह गया. Like whenever we plot the mean square error, how do we plot it? Generally in the linear regression, what we do is we have some feature here x, and we have the y value here, okay, in the y-axis. But in mean square error, in the y value, what we have is we have the error, okay, the cost or the j, which you can see. Okay, and in the x we take any weight, like in the linear equation we have this wx plus b, right? So consider we are only working with one feature, so we have a w which is a scalar value, so we have different weight values here. Okay, in the x we have weights for a like feature. And also like just to tell you all, the number of features which we have in a data set x, okay, the n which we have for the x, the same like the same size of the weights will be, like if we have 10 feature, we will have 10 weights, and we only have one bias. Okay, so this is just like to clear you all. अगर हमारे पास 10 features हैं in our dataset, then we will have 10 weight values, 10 w's, then the w will be a vector or a array of 10 numbers. Okay, let's suppose we only have one feature in our data set x, and for that specific feature we have a weight which is the slope. Okay, and that for different, like we are plotting different slope values, let's suppose 0, -10, -100, and 100, something like this. Okay, so हर एक slope value के लिए we'll get like we will put the slope value in this function, and this will compute the difference, and it will give us the error which we have, and we are plotting it here. अगर मैं like if I expand it, like in the linear regression equation we have this, right, wx plus b, and the cost function which is j, we have this sigma I from 1 till m, and y minus y hat of square divided by m, and y hat is the same thing, okay, which is the f of x, the output of this function. So if we expand it, we'll get something like this: I equals 1 m y minus I should like, I'm just keeping it in the bracket. Okay, so this is the this is the expanded form of the mean squared error function. Okay, so jab bhi like we will, what we are doing is, for plotting the mean square error, we are inputting various w values. Okay, so हम different w values डालेंगे and we will get the different errors, and which is we are plotting in here. So here what I have done is I have computed 1,000 different w values. Let's take it for the 100 values only as of now, and if I run it now, here you can see these are some of the five w values, some like sample w values, and these are like their respective cost, which is mean square error for each of the w value. Like if we input -100 as the w, we'll get this error. If we input -97, we'll get this error, and so on and so forth. Okay, now what I'm doing is I'm plotting this cost function. Now here you can see this is the plot function, which is mean squared error, and in the x-axis we have the slope, or w1, which is the weight of the feature x1. Okay, I'm only like considering one feature as of now, and here we have the MSE, which is the mean squared error plotted on the y-axis. Okay, so this is the parabola which we have. Now as I said, like we also have various metrics, which is one another, which here it is, which is mean absolute error, and this is the function for the mean absolute error. I am computing it here, and similarly I am computing the mean absolute error values for each of the w value, and I am plotting both of the graphs here. Okay, so here you can see mean absolute error is more of a V shape. Currently we have some like only some w value, so that's why it is round. If I increase the w to, let's say, 500, and now if I run it, and same if I run it here as well as here, now you can see it is more of a V shape. Okay, so as the number of values we have in x, like the more values we have in x-axis, the better graph shape we'll get. Okay, we'll get the better curve. Okay, so this is the difference in mean absolute error and mean squared error. So guys, is this clear to you all, the mean squared error, like
Yeah,
the
yeah, it's clear.
cost function?
Yeah.
Like you all might be wondering what we do with the cost function, right? So जैसा like मैंने आपको बताया था, we have the graph like this. Okay, not the pointed, this okay, sorry. uh, okay, yeah, so we have this kind of a parabola for the like mean squared error, right? And how do we basically find the best kind of, say, uh, how do we use it for like for basically fitting the model, for finding the best fit of the model, which is like okay, so jasa like here you can see, if we have like some w which is something like this, so the value, the slope, here the slope is negative, so the w is decreasing, right? Sorry, the w is decreasing, so the slope, and the slope, which is the slope, which is negative, and the line is also decreasing as the x-axis is increasing. So we have to optimize this w and the b value in such a way so that we get this red line same as the green line. Okay, so if I like tweak it with this a little more, now you can see this red line is very much closer to the green line. Okay, and also for the b, if I, let's say, if I reduce it a little, now you can see it is almost like the approximate value with the, like it is almost similar to the green line, right? So this we have to optimize. Basically what we have to do is, in the linear regression, we have to optimize w and the b. W is the weights, okay, or the slope. We have to optimize the slope values and the bias. Okay, and as I said, in the mean square error we have various w values here and the cost function here. Okay, now in the parabola, like this is the parabola, right? Can you tell me where we have the very, like, the lowest MSC, the cost, which is mean square error, at which slope, like at what value of w we have the very, like, minimum slope, oh sorry, minimum error? Can
0.
anybody tell me? um, yes, 0, right? So as it is a parabola, so like in the parabola we only have a one minimum value. So आप लोगों ने calculus में you might have learned about minimum and maximum, like local minima, global minimum, like that, right? So uh, we are like going towards the gradient descent. Okay, uh, so in the uh, here, like, we have the 0 as the minimum value, right? So let's suppose हमने जो है what we do is when we have the data x and we plot the linear regression. Okay, okay, let me write it straight once, right? So when we have the linear regression and we plot it, जो हमारी equation है wx plus b, we do not have the, like, perfect w and b value at the starting. So what we do is we start at any random w value and a random b value. Let's suppose we started with a w, let's say minus 100. Okay, and for the minus 100 we are getting the error here. Okay, this is the error which we are getting. Okay, and we know the uh, best value of the w where we get the minimum error will be here, right? So हमें जो है -100 से we have to reach this w value. Okay, and this is where the gradient descent comes into the place. Like how, I'll just tell you the, like, intuition how it works. So what the gradient descent do is it finds the slope. Okay, so at the point x, so जो भी मेरा अभी, let's suppose मेरा point अभी है -100 and it finds the slope of the curve at point x. Okay, so this is the slope, and what it does is it subtracts the slope from the w value. Okay, so here you can see the slope is like this, so the slope will be negative, right? Because the slope is decreasing as the x-axis is increasing. So it will subtract the w from it. Basically, like, if we have the w in minus and if we subtract something uh, from it, so what we are doing is we are increasing the value of w, right? And okay, sorry, like if we have some value of w, like some positive value, and if we subtract something from the w, let's suppose a, so हमारी जो value है वो new value, let's suppose w prime, it will be smaller, right? And for the negative case it will be greater. So हमें जो है -100 से to this optimal value जाना है. So what I am doing here is, like, what we will be doing here is, to basically, to get to the lesser value of the w, we are basically adding the slope here. Okay, and like, we are generally we subtract the slope. Let's suppose the slope जो है वो मैंने a से define करा, and here the slope is negative. So if we subtract the slope from here, we'll get some value in positive, and this new w prime uh, will be greater than, sorry, will be greater than the previous value which we had. Okay, so what we do is we find out the slope at the particular w. Okay, जहाँ से हमने start किया, and we subtract the slope from it, and slope subtract करके, okay, just give me a minute. So we subtract the slope, and wherever the whatever the new w value which we get, which is the w prime, we can say. Okay, let's suppose the w prime is like this, right here. Okay, we basically go from there to here. Okay, so this is the new w value which we have now. Now again we find the slope and we subtract it. Okay, and again we go to some lower value which is here. Now we have a new w, and now again we do the same thing. We subtract the slope. Okay, we find the slope, subtract it, and go to some new w value, and now again and again and again, and we do this until we, like, there are some conditions, but the general case is until we have the slope 0. Like if we have a equals to 0, and if we subtract anything, like if we subtract 0 from anything, we'll get the same value, right? So if we like do the same steps again and again for like some number, let's say n, and then we will reach a point w, which will be the minimum value. Okay, so this is how gradient descent works. And the same thing for the, like, let's suppose if I start the w, if I have the, okay, if I have the graph like this, the best value of the w is here, and if I start from here, let's suppose 100, so here also I'll find the slope and I'll subtract the slope from here, I'll get a new w value, I'll do the same thing again and again and again and again until we get the like slope as a 0. Like uh, at the minimum, at the global minimum, we have the slope as 0. ये आप लोगों ने, like, it is a fact basically, which we must have read in the calculus, right? So this is what we do in the gradient descent. Is this the intuition clear to you all? Okay, I have one more graph for you to basically explain this. So these two functions, basically you can ignore these. Let me run the graph directly. Okay, so this is the graph. Okay, and here at the w, you can see, okay, this green scatter point, this green circle is the w which we are here, and this red line is the slope. Okay, so you can see at the w equals to 0, we have the slope also 0, right? And if I decrease some w, so you can see the slope is something like this, and if I increase the value of w, this is on the cost function, which is mean squared error, and the w is like this. And I have one more graph, which is with the, okay, this slope, we call it as a tangent, right? At the red line, it is the tangent to this graph at some certain value. And the same thing I am doing here is, left graph is the same as the above graph, but on the right side we have another graph which is the derivative of this cost function. Like you know, the derivative of any function is the slope, right? So for this squared error, we have the derivative plotted here. So like if I decrease the value of w, you can see that w will be somewhere like here, and the tangent, you can see it will decrease as the value of the w increases. So if I increase the w, you will see the yellow circle, it will go upward because the slope is increased, the slope is more there. Okay, and we basically, what we have to do is, if we like start from here, let's suppose if we start from the very point and minus 500, we have to reach this 0 value. Okay, how do we reach 0? We basically find out the slope and we subtract the like slope from the w. Okay, and we reach it by like taking some smaller steps, like here I am doing. Okay, so like this, you can see I am like almost getting closer to the 0 value. Okay, right, right. So this is how gradient descent works. Okay, now, okay, let me close it. Now like this is the graph which we have for the mean square error, and we basically calculate the slope, right? Like आप लोगों ने पढ़ा होगा, for a one variable, like if we have the equation like this, wx plus b, we have the slope as w. Okay, right? And also we have the derivative of this function as w, right? Because this is a linear equation. But for like multiple variables, let's suppose like here we are dealing with only one feature, but in a data set we might have like we do not necessarily like we do not need to have only one feature, but we might have, let's say, 10 features, 100 features, or let's suppose 50 features. Okay, so we can have various number of features. So what we do there is we compute the partial derivative of the of the equation, the mean square error. Okay, and the partial derivative, normally we refer the derivative something like this, and for the partial derivative we use this term. Okay, this is, okay, I forgot what we call it. Okay, die, we call it as a die. It is a Greek alphabet. This basically represents the partial derivative, like for each like let's suppose if we have 10 features, so we will have 10 weights, and for each weights like we have a derivative. Okay, so that's why we compute a partial derivative, and all those basically each derivative will be like the partial derivative will be like we call it as a gradient. Okay, what it is a okay, sorry, sorry guys, like for the some confusion. So let me like start directly. So we have a method called gradient descent, which is an optimization algorithm to find the best value of the w. Like doesn't matter wherever we start, like either we start from here or here or here or here, we have to go to this value of w, and this gradient descent helps us in doing that. Okay, let's suppose we have 5 features, so we have 5 different weights, right? W1, W2, W3, W4, and W5. Normally, if we have one feature, we have the slope also. We have only one slope. Okay. So for that, we only have one slope. Now, for the 5 features, we have different slopes. Okay. And to basically to represent all these slopes, what we do is we store them in an array, and we call this array as a gradient. ये आप लोगों ने मल्टी वेरिएबल कैलकुलस में पढ़ा होगा. ओके, एंड दिस इज फ्रॉम वेयर द टॉपिक ग्रेडियंट कम्स इन. ओके, एंड व्हाट द डिसेंट इज, बेसिकली हम कहीं से भी स्टार्ट करें, we have the mean squared error, we have to go to the minimum value, so we have to descend like from there or like from here. Okay, so this is from where a descent comes in. Okay, so this is the gradient descent. What we do is we calculate the slope, and we subtract some value from the like w. We subtract that slope from the w, and we do it some number of times. So is this clear to you all, guys? I know thoda zyada ho gaya काफी, but it will like create the base for you all. Okay, now okay, I have some more graphs also. Like here I have a 3D graph. What I am doing here is I am taking first 2 features. Earlier I was taking only one feature, but now I am taking 2 features, and here I am doing the prediction, and I'm also like calculating the mean square error. Okay, and in the mean square, after calculating the mean square error, I am plotting a 3D graph. Here okay, here this is the 3D graph of the mean square error. Here we have the 2 different weight values. I also have like this in the notebook. If I check, okay, just give me a second, let me open it. Open. Right, if I run this, like I have a code for the same this graph. Okay, this is a surface plot. This is the same as this, but this is in a 2D. Okay, and it is for only one uh, variable, which is w. Okay, w1 we can say, but this is for 2 variables, which are like w1 and w2, and on the z-axis we have mean squared error, and the same thing I am doing here. This is the same code. Okay, and if I run it, okay, yeah, so here you can see this is the same graph which we have in the notebook. Okay, Kaggle notebook. So here we have 3 axes. This is the x-axis, which is weight w1. This is the y-axis, which is weight w2, and on the z-axis we are computing the mean square error. Because this is a parabola, so in a 3D plot also it will be something like a bowl. Okay, so if you see it from the top or like from the sideways, it will like, it looks like a bowl, right? A bowl shape. And here like I also have a scatter point, which is this red dot. This red dot is the best w value. Okay, best w value for both w1 as well as w2. Okay, you can see from here also, and this is the minimum value for this graph. Okay, and I also have like one more plot, which is here, right? So this is the same plot, it is just in a different color palette. Okay, uh, what I here have is, I have two sliders, which is w1 and w2. These are two different weights, and we have two scatter points, red and green. Red represent the best w value and green represent the current w1 and w2 value. If I decrease the w1 by like some value, you will see the green will come here. So here you can see this is the green, and the red is somewhere like there. We cannot see it like properly, but I hope you can see it a little bit. So yes, and if I like increase the value of w2, you will see the green will go there, like somewhere here, right? So this is how like what we generally do is, in gradient descent, we find out the slope and we decrease the value of w by like some little, by the slope. Okay, and we do it again and again until we reach a minimum value. Okay, so here for w2 we have 45.45, so I am just reaching here. Yeah, so at 40 we have the, like, we're almost in the same axis, if you can see here. And similarly for the w1 also we'll do the same thing. Okay, yeah, almost there. So now you can see both, like the green circle and the red circle, both are on the same point. Okay, so this is how gradient descent works normally. Okay, now for the, like, okay, अभी तक किसी को कोई confusion है? Guys, do you guys like have any kind of confusion? Okay, now like I know बहुत सारा theory हो गई बहुत सारी. Now let's come into the code. Okay, so what we will today, like as I said, we will implement the complete linear regression from the scratch. Okay, just before that, I just want to tell you there are two ways to do the linear regression. First one is the normal equation way, which is this equation. We basically multiply, do the matrix multiplication. We multiply the matrix with the transpose and inverse it, and then again multiply it with the transpose and then the target label. Okay, then also we get the optimal values for the w. Okay, and then we have another way, which is gradient descent, which we have discussed right now. Okay, so we are like implementing this gradient descent way, which is like uh, more important compared to the normal equation one. Okay, so let's start. These are like this, let's start from here. This is the table for the notations which we have. Okay, now what I'm doing here is, let's first like do for the, okay, yeah, let's first do for the first one feature only. Okay, so here we have like 1000 samples, and we have like their respective y value, and we only have one feature, so this is only like a one, you can say, in the array we only have one value. And what we are doing here is, we are basically splitting the data set into training and validation set. Okay, and the linear regression equation is this wx plus b. Okay, this is what we are implementing right now. Okay, let me just get rid of this. uh, I'm just defining the function here.
Could you go slightly slow because
Yeah,
we are
sure.
unable to see?
Okay, uh, this, are you all clear with this? Okay, sorry. This, here we are generating 1000 samples. Okay, x and y with only one feature, n equals to 1. Okay, so this is the sample data for the x, and this is the sample for the y, which is our target label. Okay, is this clear?
No, sir. That only x having 1001. Uh, in
Okay.
the first array, what is that? It is m. It
This is
is.
m. M is the number of training examples we have. Okay, let me zoom it more. Now it is clear.
Yeah.
Okay. Noise, oh yeah, I will tell you. And then we have the n, which is 1. So noise parameter basically tells us how much our data should be spreaded. So like if we have noise equals 0, and if we call the make regression, we'll get the points which are like more closer to each other. If we set noise to some like some positive value, we'll get the data more spreaded. Okay, so this basically helps us to create the some random or a fake data, we can say. Okay, that's why we use the noise parameter. Now what we are doing here is, with the help of 1000 examples and one feature, we are creating a data set, and this is the like first 5 samples of the data set, okay, for the x, and this is the first 5 samples of the target label y, okay, out of 1000 samples. Is this clear? Till now it is clear, guys? Okay, I
What
think
are all the weights of that particular equation?
I'll tell you. Okay, currently we are just like defining the data. This is the data we have, x and y, and what I'm doing here is I'm splitting the data into two parts, which is x train and x valid. Okay, 20% in x valid and 80% in x train. Okay, and if I run it here, you can see out of 1000 samples, 800 will be in training and 200 will be in the validation set. Okay, is this clear?
Yeah.
Param, wait, hello.
Yes, yes.
Uh, then how much in test data set?
No, we only have two data sets, which is x valid and x train. The test side is the parameter. Okay, we can
Okay,
either
okay,
name x
okay.
valid as a x test, but I am just naming it as a validation set. Okay, uh,
Test size is just a parameter, not about the
right,
test
right.
data set. Thank
So
you, thank you.
yeah, now this is the linear regression equation, which is wx plus b, right? Fx and wx plus b. We input the x and we get some y value, which is y hat here, and w is the slope and b is the intercept here, right? Now let's implement this equation in the graph, oh sorry, in the code. Okay, what I'll do is I'll simply write I'll create a function linear regression, which basically takes three values, which is x, w and b, and what it does is it computes the same thing, f of x. Okay, how uh, there is like okay, one thing like I want to tell you, like if we have the only one feature, then our data will be something like this, right? And same for the like, then we only have the weight as a 1, so this will be a like a vector to scalar multiplication. Okay, and if we have multiple values, like okay, we have multiple let's suppose say features, then we have a matrix as a data set. Like for the 5 we have first value here for the first feature, and the value for the second feature, and so on and so forth for the like all the samples. And in the w parameter, the weights will have a vector or a array of the weights. Okay, which will be something like this, and the shape should be same, right? For the vector, we it should be something like this, m into n, and here this n into 1, and the similarly n into 1 and the m into n. This is just for the one feature, and this is for the multiple features. And here what we are doing is we are multiplying a vector by a matrix. Okay, and here we are multiplying a scalar by a matrix in a one feature and a multiple features. And in doing the matrix multiplication, we have like various methods, and one is matmul, and dot also, like we can also compute the dot product like using the dot function, np dot dot. and there is a shorthand for it, which is at the rate. If I write x at the rate w plus b, it will be it is same, it is similar to the doing the matrix multiplication between the vector and the matrix. Okay, so this I am doing here because like to align the vector and the matrix in the same space, I'm writing x first and then the w. Okay, and this is our linear regression function. So is this clear to you all? Guys, is this clear? Okay. Now just like as Pawan asked, where are the weights defined? So we are basically starting with the zero values for the weights. As I said, हमारे weights कुछ भी हो सकते हैं, any kind of random value. So we are starting the weights from the zero value. Okay. Here we have only one feature. Okay. N equals to 1, so our w will be an array of only one value, and b will always be a scalar value. Okay, so these are the weights and bias. So is this clear, guys?
Yes.
Okay, now comes the next thing, which is implementing the cost function, which is the mean square error. Let's implement it. So what I'll do is I'll write def compute msc. Okay, and in the mean square error, what I'll do is like I can either pass the whole equation, which is fx plus b, like I can either pass these three parameters, or I can either pass the predicted value. What I'll do is I'll choose the expanded form, where I'll simply pass x wb as well as y. Okay, and here like let me extract the shape of the data set. If I do x dot shape, I'll get the number of features and the number of samples and the number of features in m and n respectively. Okay, now this is a like we are summing over, or what we are doing here is we are subtracting the actual value and the predicted value, and we are squaring it, and we are doing it for all the like m values, for all the m training examples. So what we will do here is we'll run a loop. Okay, for I in range m, and for each of the m sample, like for each of the m, what we will do is we'll compute the f of x. Okay, which is the basically linear regression. We can directly write it as like this, y hat, and I'll simply call linear regression here, and I'll pass x, and in x I'll only pass I, and yeah, that's it. I'll only pass the ith sample, and in w I'll pass the complete data as well as on the b. Okay, then I'll get the y hat, and now what I'll do is I'll compute the difference, which will be any like y hat, my I can do in any way because I am squaring it at the end, right? I can do it in this way, or it will be similar to like this also. Okay, y minus y hat or y. Now what I'll do is I'll do the square, which will be difference raised to power 2. Okay, this will be the square, and now I am summing it all over. And how I'm summing it, let me write it as total equals 0 and total plus equals square, and after summing it I'm dividing it by m. Right now just see the m1, like you can ignore the 2 which I have written here. I'll tell you why I have written the 2 here, and what we will do is divide the total by m. Okay, let me like just clear you all with the 2. Basically we have the power here, right? And when we take the derivative of this function, we'll get the 2 above in front. Okay, and to cancel out that 2 with this, to cancel out that 2 in the derivative, we are basically having the 2 here. Okay, so that 2 cancel out this 2 when we take the derivative, so that's why I'm taking the 2 here, and it doesn't like interrupt in the equation. Okay, so it doesn't much affect the mean squared error. Okay, and now if I run it, so this will be the my mean squared error function. And what I can do is I can like the weights which I have right now, I can check the error which we have. okay, based on the weights we have initialized. So what I'll do is I can simply write compute MSC, and I'll pass the X train, W as well as B, and Y train. And if I run it, okay, I'm getting the error unsupported for the okay, in the linear regression I have to return this also, f of x. Right, now if I run it, now you can see I'm getting this okay, this is a little different, sorry. Okay, y hat minus y, the same thing which I was doing. Oh, sorry. Basically I'm getting the y hat for this single example, and y is the complete data set, so I have to subtract only from the ith example. Now if I run it, I'll get a single value, which is the cost or the mean square error. Okay, so currently the mean square error is 137.09, and the same function I have implemented here. Okay, we can also implement it in a short way, which is like using the numpy functions we have. Okay, and let me run it also. And then we have the gradient descent. In gradient descent, as I said, what we do is we subtract the slope, which is the partial derivative of each of the weights and the bias. Okay, the this dj, which you can see here, j is the cost function, and in the denominator we have the weight, and similarly for the bias, so this is the derivative. And we also have one more thing, which is alpha. So alpha is the learning rate. And what is learning rate? Let me tell you. Let's suppose we have this okay, sorry, just a second. Yeah, so let's suppose we have this mean squared error. Okay, parabola, right. Now this is a mean squared error, and let's say like we started from here, some w value, and we have to go there. Okay, we are just finding the slope and subtracting it. Now like जब भी हमारी w के value, like whenever the cost will be high, the slope will be like higher. The value of the slope will be high, doesn't matter whether it is in a negative or positive, it will be some higher value. Okay, and as we go down and down, the slope will decrease and the steps will become smaller and smaller. Okay, and it will take like a lot of time to reach to the w. So this thing we handle, like this is a problem which we face. Okay, and this thing we handle via learning rate. What we do in learning rate is like basically normally what we do is we subtract the slope directly, which is the dj over dw. Okay, this is the derivative for, you can say, for this w parameter, we simply subtract it. What we can also do is we can add an additional parameter alpha. Okay, and we multiply the alpha with the slope we have for the respective cost function and the w value. And what this alpha helps us, uh, like what this alpha do is, it basically, okay, sorry, yeah, alpha basically controls how much should we like subtract from each of how much should we subtract in each value. Let's suppose if I set alpha to 0.1, so if I get let's say if I get the slope here as okay, for this point, if I get the slope here as minus 100, okay, then with the alpha parameter 0.1, I'll only subtract w minus 10. Okay, because I'm taking only the 10% of the slope, so I'll only subtract some value, and the similar thing will happen here and here and here, and it will like basically helps us to go reach to the minimum value more better in a more efficient way. And there are like, this is a hyperparameter, and here comes the hyperparameter part. What a hyperparameter is, we can basically try different values for this, and it affects the basically our complete model. How? Let's say if I set the this is my graph, and if I set alpha to some bigger value, let's suppose 2. Okay, what it will do is whatever the slope I'll get for the point w here, it basically increases it by 2, and it takes some bigger step, and then again, and then again. And let's suppose our minimum value of w is here, but because of this higher value, it basically crossed this minimum. This is the problem of, like, we can say this is overshooting the minimum. Okay, and it basically go on and do the same thing like again and again. And similarly, if we set it to more some like higher value, let's suppose alpha equals 5, and this is the parabola. Let's suppose we started from here. Okay, then it will take very much big steps, and it will basically cross the minimum value, which should be somewhere here. So this is the problem of overshooting. Okay, so that's why we have this alpha as a hyperparameter. Okay, this is the
Alpha is
0.1.
same,
Sorry.
alpha is same as this eta.
Yes, alpha is the eta which we have in our linear regression. Okay, eta, alpha, we call it in various names. Generally, these are the two names we define. Okay, and the normal, like, the suggested value for the alpha is should be like we start from 0.01, and like we try various values. Let's say we try 0.03, we try 0.09, and basically it's the multiple of 3, we are multiplying it with the 3, and we try 0.1, 0.3. So we generally keep it in the range of like 0.0012 to 0.1. Okay, so this is the suitable range for the alpha, and we have to tune the alpha. This is where hyperparameter tuning comes in. We use various alpha values, and we find the mean square error. Whichever alpha value gives us the lowest mean square error, it is the best value. Okay, so are you all clear with the alpha, like the learning rate?
Yes.
Okay, now this is the gradient descent. Okay, this is the equation, and for each of this the derivative we have here, like for the like, okay, let me write it here. This is my cost function, right? uh, y minus y hat square divided by, and I am just using 2m because just to cancel this. Okay, and if I write it in an expanded form, I'll get something like this: y minus wx plus b, and here square, and this is 2m, right? So this will be the expanded form, right? Now if we take the derivative of this equation, this is the j. Okay, if we take the derivative of j with respect to w, what we will get is, we'll get this value. This is for all the examples, training examples. Y minus and here I'll get the, okay, yeah, here for the w I'll get the complete, like, uh, okay, sorry, the derivative basically, the derivative for the this will be x, and the x is in the like minus, if we see here, because it is in, we are subtracting it, so minus x. Also, like the square, we have the square here. This is basically a chaining rule which is happening, and this 2 will come here, and it will be the final derivative will be minus 2x. Okay, and we have like 2 here and here also, so that's why, like, we add 2 in the denominator of the cost function to basically cancel from the derivative. Okay, and the same thing we have here for this. Okay, for respect derivative of the cost function j with respect to w, we have minus x, and for with respect to b, we have the as it is, the function as it is. Okay, and these are the partial derivatives, and this is like due to the chaining rule. If you do step by step, you will get this exact derivative which is written here. Okay, and the same thing, let's now compute the derivatives. Okay, and as I said, if we like, here we have multiple features, like we are basically creating the linear regression for multiple features, and for multiple derivatives, multiple slopes, we store them in a vector, and that vector is known as gradient. Okay, so let's like implement the gradient function. Let me write like this: def find gradient, and in the find gradient I'll simply pass the x, wb as well as y. Okay, and let me just extract the number of samples and shapes we have. Now for each of the uh, w and for each of the b, I need like I need to find the gradient. Okay, and how? I'll simply write dj dw, which is 0, and dj db, which is also 0, and I can also write for the dj dw as like this: np dot zeros, and the shape will be n comma 1, because the w will be of the shape as the number of features we have, right? And the bias will be 1. Okay, now to find the gradient, we have to like go over to like all the training examples, and for the w value, we have to compute the mean square error, and then we have to like find the gradient, and basically subtract. Okay, here we have this. Yeah, basically we have to sum of all over the training examples. Okay, like हर एक training example का we will find the gradient and we will sum it over, and then we will get the final gradient for the w and for the b. Now let's implement this for I in range m, and let's first find the fx, which is linear regression, and in linear regression I'll pass x of I as well as w.
Actually, np dot zeros of n comma 1.
Mm-hmm.
So what actually it used to do?
Okay, if I
It
run
is
it,
n by 1 matrix, right?
right, n by 1
We
matrix,
place one column with 1,000 zeros.
right,
Okay.
thousands, or like the number of features we have. Here we have n equals 1, so
Yes.
we'll get only 1. So because like we have a w as a gradient vector of slope, so that's why I'm creating a array rather than a scalar value 0. Okay, then what we do is, after basically finding the linear regression, which is y hat, we basically compute this dj underscore dw. Okay, for okay, let me write it as like this: grad w. Okay, which is the gradient of the with respect to the w, and this will be y minus y hat. Okay, so yeah, y of I minus which is f of x, which is the y hat. Okay, f of x or y hat, it is same, and what we are doing is we are multiplying it with minus of x value. Okay, this we are doing here, and then we will do find the gradient for the b as well, grad b, which will be like just the subtraction, nothing more, because we are basically also like the minus also, uh, because we are subtracting it, so that's why minus. And because this is the gradient, so we are simply writing the gradient here. Then we will add the gradients in the respective variables, so dj underscore dw plus equals grad w dj underscore dw plus, sorry, db plus equals grad b. Okay, and this is for like all the training examples. We are adding it, we are summing it up, and then after that what we are doing is we are dividing it by m. Okay, which is the total number of samples we have. Here you can see, and same for the b. So this is okay, not m, yeah, w, and we are returning it here: dj dw dj db. So this will be the find gradient function, and the same function I have implemented here, which is this. Okay, so both are same, no difference in this. And if I like currently for the value, for the 0 W values, where I got this mean square error, if I find the gradients, okay, for this respective W value, let me do it. Find gradient, and I'll pass X train, W, B, and Y train, okay, and it will find the gradient for me. Okay, runtime morning divided by 0 and coinciding. Okay. Uh, okay. I have to divide it by M and N, not the W and B. Yeah. So here you can see, I got this. So this is the slope. Okay, this is the basically gradient I got for this W value 0. For the W0, I got this as the slope gradient, and for the B as the 0, I get this as the slope. Okay, so these are the gradients. This is the W and this is the B, and the same function I have implemented here. Now we have calculated the mean square error, we have calculated the gradient. Now the last part is to combine all of this in the gradient descent. Okay, to basically to iterate it all over. So okay, there is also like one more parameter, let's suppose we started from here. There is like some concepts which I am just telling you. There are like, sorry, these are very short concepts. uh, One is epochs. Epochs are basically number of iterations which we do. Okay, what are number of iterations? Number of iterations are like basically how many steps should we take. Like let's suppose our W is this and we are starting from here -100. Okay, and let's say we have epochs as 5. Okay, so let's say we started from here, we take one step, we take another second step, we take 3, 4, and 5. Here we have set 5 like epochs as 5, so we'll stop at here only. Okay, so this will be our like the W which we have found. So this is not a hyper parameter, but this we set as the number of iterations which we have to do generally. And then let's suppose if we set epoch as 10, then we can also take further more steps and so on and so forth until we reach the W. Okay, and there comes one more thing, which is the problem of convergence. And what is that? uh, let's say this is the graph. As I told you, like जितने भी हमारी higher value होगी of the y-axis, the slope will be much higher, right? So the steps will be bigger at starting, and it will decrease as we go down and down and down. Let's suppose if we set epochs as thousands, number of iterations as 1,000, so it will take 1,000 steps. But even with the 1,000 steps, when it go to the like around minimum value, the slope will be very minimum here compared to this slope, right? So it will take very small steps and it barely reaches to, let's say, this. Okay, after taking the all the 1,000 steps, it reaches there. It is not the W, but it is closer to the actual W. So this is here we call our model as converged. And like this is just by the graph we can say our model is converged. But like here, if I, okay, I'll take this graph only. Here you can see these are the like various cost values, and by taking these small values we are only getting a very little difference in the cost. Okay, and whenever we have like zero difference in the cost or very little difference, we can say our model is converged there. Okay, so these are the two cases. Basically the case is similar, we are just checking it from different angles. So this is the problem of convergence which we face in gradient descent. You might have encountered in logistic regression or in linear regression while modeling, like convergence warning, our model is converged, right? Set max number of iterations, iterations to some higher value or something like that. So this is where the convergence warning comes into the place, and that's why we set the number of iterations to a bigger value. Are you all clear with this concept, the number of iterations? Okay. Anybody has any doubt?
Hi, Parampreet.
Hi,
I'm sorry I couldn't join your class today, although I wanted to.
no
And
problem.
again, I have to join the other live session by the instructor. But
Okay.
I just have one request. Can you share this file in the group, this collab
Uh,
file?
this Kaggle notebook, yeah, I will share this after the session in the video recording,
Okay.
in the
And
YouTube
thank
video
you so
response.
much.
Yeah.
And also, can you tell me the resource from where you're studying all these?
Okay. I studied this like I think 2 years ago before starting this degree. There are many courses.
Hmm.
I'll tell you in
Okay.
the uh, in the group. Okay. I'll share some
Okay.
resources from where I have learned.
चलो ठीक
Although
है
they are
because
public,
हाँ
I'll tell you in the
one
group.
okay you tell us the resource okay that will
Yes,
be
sure.
helpful okay thank you bye bye.
Welcome. Okay. So yes. Uh, Now the one thing which we are left with, implementing the gradient descent complete. Like we have finded the gradient, we have the cost. Okay. And now what we have to do is we generally have to combine all of this into one, which is the gradient descent. Okay. Now let me simply create a one more function here, which is uh, I'll simply name it gradient descent, which is the same name as below. Okay. And in the gradient descent, like as you can see in this equation, we have various things. Like let's start from the basics. We have w, x, and b. We have three things. Also we have y value, which is the actual true value. Okay. And then okay, then if we go ahead in the gradient descent, we have one more thing, which is alpha, which is the learning rate. Okay. And as I told you, to take the number of steps, we have one more value, which is the iterations or the epochs we take. Okay. So let's write all these parameters here which we need: x, y, w, b, and alpha and epochs. Okay. So okay, let me just now this here I'll be implementing the gradient descent function. Okay, it will be similar to this only. I'll tell you how it works. I'll implement it. Okay, don't worry. So let's first start with the basic, which is taking the shape of the data set. Now uh, for the w, let's define the all the w values which we'll get. Okay. uh, okay, not get, basically which we will be have, which we will have at the end, we can say. Okay. What we basically we don't here we are passing the w and b as it is. So what we are doing here is we are creating a copy of it. Okay, I am using the deep copy function from the copy module. Like there is a module in Python which is copy. Okay, and in this we have a deep copy. Deep copy basically copies the complete data structure from the like very end, so there won't be any kind of similar pointers, you can say. Okay, I'm just copying it as of now for the b and as well as for the w, because we have to update this w and b. Now what we will do is
Come again, sir. This deep copy, na? Deep
yes,
copy.
this deep copy basically it is for copying the weights and bias, and we have to change the weights and bias. Basically we have to update the weights and bias here, right, according to the gradient descent. So हम जो है ओरिजिनल वेट्स एंड बायस को चेंज ना कर दें, दैट्स व्हाई आई एम क्रिएटिंग अ कॉपी ऑफ इट. ओके. Now
Okay. Okay.
if I run it for I in range, I basically have to run it. Okay, not for the like number of examples, but now what we are doing is we are directly running for the total number of epochs. So I'll simply write for e in range epochs. Okay, and for each of the epochs I'll compute the f of x, which is linear regression, and I'll pass x, w, b. Okay, and then I'll do the compute gradient one. I'll call this function compute gradient, and I'll get two values which are dj the gradient respect to w and the gradient respect to b. Okay, and I'll simply write compute gradient, and in this I'll simply pass, okay, what I have to pass, x, y, w, b. So x, y, w, and b. So right now we have like called two functions, basically combined two things, and now we have one thing which is this, do this updation step, which is basically subtracting the gradient from the actual w value, okay, with the alpha parameter. So the same thing we will do here. W equals w minus okay, before doing this, just want to tell you, like okay, let me do this as it is as of now, into alpha sorry, minus alpha into dj dw, and the same thing we will do here, b minus alpha into dj db. Okay, here we have computed the gradients, so the problem which I thought will arise, it will not, because we have already computed the gradients earlier. Okay, now we have done this updation step, which is this equation. Okay, and these are the derivatives we already computed here as in gradients. Now we are basically running it for the number of epochs, and after running it for the number of epochs, basically our gradient descent will be completed, and we will come with the updated parameters of w and b. So it will return the w and b as of now. Now I have called basically run this function. Okay, I have called basically executed this cell. Now let's run this function. We have w here like this, okay, and b is this all. So these are the initial weights, initial parameters, and x and y we already have, we have already defined like this. X train is this and y train is this, right? Now let's set some more variables. One is alpha. As I said, alpha we set from 0.0001 to 0.1, so I'm just setting 0.1 as of now. Okay, now let's set one more parameter, which is epochs. Epochs are let's say we are setting only 100 as of now, or let's suppose 10 only. And alpha, alpha or ETA, like as someone said in okay, alpha or ETA, like this alpha, or learning rate, these are all the same things. Okay, we can name it any uh, way we want. Okay, so I'm just writing it in another notation, which is learning rate, and the epochs are number of iterations. Okay, so these are the number of iterations we have. And now let's run the gradient descent function. So what I'm doing is I'm just writing gradient descent, passing in the x, y, w, b, learning rate as in alpha, and iterations directly. Okay, so I'll get the best value for the w and b after like doing this. So these are the parameters I have passed in the same way. Now let me run it. So now you can see I got these two values. First one, this is the w, and this is the b. So these are the best w and b values for our data set for the feature one. Now like to check this, how can we check this? Basically what we can do is, let's simply plot the graph. So yeah, x train and y train, if I plot it, so okay, this is the, yeah, this is the scatter plot which I have here. Okay, let me just plot it for, let's say 50 samples, and same for this. So these are the, like, this is the scatter plot which we have. Okay, this is for the only one feature. And now let me plot this, let me use this equation and plot the line. What I'll do is I'll write plt dot plot and x train into, okay, x train of 50 into this value, which is 10.63. So I'm just writing 10.63 plus 0.13. I'll just round it off to 13. Okay, 128. And if I run this, okay, I have to pass it. Okay, so this is for the x-axis, so I have to pass in the x-axis also. So yeah, this you can see this line. Okay, let me color it also to some different color, green. Now you can see this green line is the line which we get from this these weights. Okay, and let me label it also best fit. Okay, also let's plot another line which is by initial weight. So initially we have weights 0, right? So if I just simply write it as 0 as and 0 here, and let me use red, and you can see earlier we have this red line, but now we have this green line. Okay, so this is how it is basically calculating the best values for W and B. So this is the complete working of the linear regression. And now, as I said, the number of steps we take, the better we can, like, the more closer we can reach to the minimum value of the cost function. So if I set iterations to 100, and now if I run it here, you can see it takes some time, and now I got this value. So if I set it to like this value 74, and in the bias let me set it to, okay, it is 0, so I'll simply set it to 0. And now if I run it, you can see this green line is completely 100% accurate to the data. Earlier we had okay, let me copy this this, let me set it as yellow, and this is green. 16.7, I'll say 5, also 0 here. So you can see the red line, we started from the red line. After 10 iterations we got this yellow line, and after 100 iterations we got this green line. It doesn't mean like 100 iterations ke baad hi we'll get this green line. It can be like any number. If I simply set, let's say 20, so in 20 I'm getting this value, and if I set this value here 14.51, so now if I run it, you can see this is almost closer to this, and it eventually depends upon the number of iterations. Okay, so now I'm getting some better value, and so on and so forth. I'll get the exact value, which is this. And abhi jo hai, like, we also have this is the number of iterations. Now we have what we do is we generally hard code the number of iterations. And what we generally do is we take the, like, we tweak with the learning rate. So if I set learning rate to 0.1, and let's suppose at, okay, with the 0.1 and this, we are reaching this value, which is the approximate correct value. Okay, so this is the green line, which is, you can say, the best fit as of now. And if I set the learning rate to 0.01, now you will see I'll get a very less value for the W, which is 6.3. And if I plot that value, which is 6.3, you can see this is the yellow line. So that's how learning rate affects. If I set learning rate to 1, and now you can see I'm directly getting like the exact value. And if I set learning rate to 2, I may overshoot it. So as I said, like, we may overshoot it like this. Okay, and that's why we're getting a 11 as the W value, but the optimal value should be around 16. Okay, so this is how learning rate affects the model, the linear regression model. Okay, is this clear to you all? um, Yogendra, Ritik, Rohit?
Yes, yes.
Okay. So now what
Yes,
I have
madam.
done here is, like, this is the same gradient descent function. What I have just done here is I have added the, like, I have computed the cost at each W value, as well as I have also stored the respective W and P also, like, to plot the mean square error graph. Okay, so now here you can see I have number of iterations, let's say 100, and alpha as 0.1, and I am running it. Now you can see at iteration 10 we have this cost, and at iteration 20 we have this cost, iteration 30 we have this, 40 this, 50, 60, and after 80 you can see 80, 90 and 100 we don't have much difference in the cost, right? It is 3211, then we have 3205, then 3204. So we can say our model is converged at 80 iterations, right? We can say that. Am I right? Like based on the cost we have.
Yes.
Okay. There is like, if I, let's say, let me, yeah, currently as of now 100 only. And if I basically plot this graph, uh, you can see this is the cost. This is the graph of this cost, okay, which I am printing here. You can see it is starting from here and going down, down, down till down this. So this is 1 raised to power, sorry, 10 raised to the power 7. Okay, IE7, this denotes this. So we are getting very low cost here. And now if I plot the cost with respect to the W parameter, you can see this is almost like a, like this is the half of a parabola, right? How you can get the complete parabola? If I, let's suppose, if I set it to 200, and now let me plot it. Okay, now also it won't, yeah, I have to increase this W values also. So if I, let's suppose if I set the alpha to some bigger value, and generally you can see like here I have set the alpha to 2, okay, not even 2. If I set to alpha to 1, okay, let's suppose 1.8, okay, okay, now also the cost is decreasing. Let's say we set the alpha to 2, which is the learning rate. Now you can see the cost is increasing. So this is where the overshooting is happening, like this. So if I simply plot it, you will see a very weird graph. So this is the oscillation which is happening. What it is doing is, like if I show you step by step, this is the parabola which we get, right? And uh, because I set alpha to 2, it is like starting, let's suppose it started from here, it takes a very big step which is this, and then again it takes a very big step which is this, then again this, then this, and then this, then again this, something like this, and it is going up like this. Okay, it is a zigzag kind of. So that's why we set alpha to a very lower value. So if I set to like a very good value, with, let's suppose if I set in fact to 1.9, I'll get the histogram like this. You can see this is the oscillation happening for the W. Okay. Now I'll simply, let's suppose if I set to alpha to very small value, this is 10 raised to the power minus 5, you can say. Okay. Now also the cost is same. Why? Because it is taking very smaller steps. If I set alpha to very small value, like I have set here 0.0001, and this is the graph, it will take very small steps like this. Okay, so we should set alpha to some very good value which should keep our basically which should decrease our cost effectively. Okay, so here you can see this is the W value, which is of course not working as we need. So that's why we set alpha. Let's suppose if I set to 0.001, and if I plot it now, you can see now, okay, now also it is decreasing, but now it is decreasing with a higher rate. So that's why we set alpha to some good value. Let's suppose 0.3. Okay, then now you can see this cost function graph is a curve. It is the number of iterations and the cost we have. Same for if I plot for the W, you can see I'm getting a curve here. Okay, this is how basically gradient descent is working. And now you can like I'll share this notebook with you all, okay, in the video description. Just copy it, okay, create a copy of this in your Kaggle account, and after copying it, just play with these parameters, set iterations to, let's say, 100,000, 10, 20, 1, okay, and for alpha set it as like 0.001 or something like that. Try various parameters and choose the one which is working best for you, okay. And now as I said, we had like we started with one feature. Now let me set it to 5, okay. Now you can see my sample is of like 5 features, and let me divide this, and after that let me initialize the weights also. So these are the weights, first 5 weights, okay, w1 to w5. And now if I compute the cost on these weights, you can see this is the cost. And if I do the gradient descent, if I run the gradient descent on it, here you can see this is the cost from where it started, and the cost now it is now we got is this, okay, 14532. Now if I set like alpha to 0.1, which is a higher value, you can see our model is almost converged. If I set it to, let's say, 150 iterations, you will see like after the 90th iteration our model is converging because we are getting almost same cost, 3 with a very low difference, okay. So that's why like setting number of iterations is also good, but we generally we hardcode the iterations, and we play with the alpha parameter, which is the learning rate, because eventually it only this will affect the model, because we are decreasing based on it. And here you can see this is the parabola, like half parabola which we got. So this is it almost, okay. And the convergence and overshooting which I told you here, the points I have written. And then there comes the regularization. This is just a 10 minutes part, okay. What regularization do is it basically minimizes the weights, okay. There are two types of regularizations. One is lasso, which we call it as L1. It basically, the formula for this is this, lasso regularization is this. It goes over all the weights, and it uh, finds the absolute value and multiply it with some lambda, okay. Here you can see this lambda parameter, it multiplied with some lambda, and we add this regularization,
Ranjit,
the cost function. Yes.
this is also in quiz 1.
Yes, this is in the week 4 regularization, lasso and
Okay.
ridge regression, which you have seen, okay.
Mm-hmm. Okay.
So the lasso regularization, the formula for this is it basically takes the absolute value, and uh, two basically features you can say for the lasso is it basically shrinks the weights to 0, okay, and it is not differentiable because it is taking the absolute value. So of course you can say it is not differentiable. And then we have another regularization, which is ridge basically squares the w. uh, okay, what we do is okay, why we are doing the regularization, because we might have like various, like when we have a lot of features, we don't know which features are more useful or which features are like uh, should work better with our model. So what we do is we use the regularization, which basically minimizes those weights values to almost 0, so that the features which are like not much useful in our cost function, okay. And this is the basically these are the function this is the formula for the regularization. This is for lasso and this is for ridge. And ridge basically changes the weight by a smaller difference because we are squaring it and multiplying it with the lambda parameter. But lasso basically shrinks the weight to almost 0. And now like in PYQs you must have seen like they have implemented a ridge regression, and they have asked what will be the weights, like उन्होंने 3-4 options provide किए होते हैं, and you have some weights in each of the options. Now you have to choose. What you can do is, if you like see some of the weights are 0, you can instantly say like this is, we are implementing the ridge regression, sorry, lasso. Okay, it was lasso, I think. Um, Lasso regression leads to 0. Oh yeah, right, it is the lasso. Whenever like if they say the weights are, some weights in the options are 0, then you can say we have implemented the lasso regression. Okay, if the weights are like in points but closer to 0 but not exactly 0, then you can say we have implemented the ridge regularization. And in scikit-learn we don't have to explicitly write the regularization. What we do is we can either like, there are various things, like if I show you from sklearn dot linear model import, generally, yeah, I just want to tell you some things. First one is this. Okay, linear regression. So if you generally import, use this linear regression, this is the linear regression from the normal equation which I told you here. Okay, this equation works. This is the normal equation. This is how linear regression works. If you use this one, okay, if you want to use this gradient descent one, then what you have to do is you have to import okay, you have to import sgd regression, sgd, sorry, sgd regressor. So this is the stochastic gradient descent. So you no need to go, there is no need to go into the definition of like what is stochastic gradient descent. It is basically taking all the samples at once. Okay, and this is the basically for the stochastic gradient descent. And then we have some more also. One is ridge, okay, and the other one is lasso. So we can simply, these are also the models, but these are with the ridge regularization inbuilt, and this is with the lasso regularization built in. So we can directly use it, or what we can do is like in the SGD regressor or linear regression, we can like while calling, like while creating the model like this, when we create a model like this, we can like we generally pass the alpha, which is the eta, you can say, learning rate, right? Similarly, like passing similar to alpha, we can pass the penalty. Okay, penalty is same as the regularization. This is just another word. So L1 is the lasso, L2 is the ridge. So by default penalty is L2. You can also set penalty to L1, which basically uses the lasso regression instead of ridge regression regularization. Okay, and you can also like, there is one more penalty which is um, elastic net. Okay, what is this? It basically uses both regularizations together. Okay, it uses ridge and lasso together, and the cost basically the regularization affects in the cost function. Okay, and we have to minimize the cost function at the end, so that's how it works. And elastic net basically combines L1 and L2 together. Okay, so whenever like we are not getting some good result in the linear regression, what we can do is we can implement both regularization together by passing this elastic net parameter. If we see here in the penalty, we have L2, L1, elastic net, and none. So the penalty is the regularization term, defaults to L2, and then L1 also. Elastic net basically so elastic net basically takes both of this, both of the L1 and L2. Okay, and this is the regularization. Uh, so like this is how you can use these parameters. And one more thing, like in the questions you might have seen one parameter which is warm start, right? What warm start basically do is it basically we are doing the, we are basically noting down the each step in the gradient descent. Okay, So warm start, if we set warm start to some value, let's say 0, and then we do fit, whenever we call model dot fit now, it will take each step. So the number of times we call model dot fit, it will be similar to a number of epochs we have. Okay, so whenever warm start is 0, you can say we are only taking the gradient ones. We are only we have set epochs as 1. Okay, let me tell you once more, like if iteration is like here iteration is 1, so iteration 1 basically similarly it means warm start is 0. Okay, so warm start is true, so that is what warm start do. Are you all clear with this? I know thoda sa regularization का ज़्यादा हो गया,
Yes.
but just to cover up the concept. So
But in examination,
mm-hmm,
when question will come,
mm-hmm.
then we have to add or multiply the matrices, right? We don't
No,
have to
no,
exactly put this
not
formula.
necessarily. You have to multiply. Basically, they just ask about your intuition. Like I saw a lot of PYQs where they are asking, like they have implemented the lasso and they have like some weights in the options and they are asking which will be the suitable weights. So if you know, like lasso shrinks the weights to 0, so whichever option has the 0 weights, that will be the best option for you. So they won't like, they will ask for values, but not like you have to implement the gradient descent, you have to do the like find the derivative and do all the stuff. They might ask you for one variable because it is easy for the one variable, and maybe for two variable, but not for like multiple variables and all. And you don't need to do the matrix multiplication.
No.
Okay, is the like all the concepts clear which we have like done today? Guys, if you have any doubt, you can ask me.
What are R2 and accuracy type of things are
Okay,
there
yeah,
in the
yeah,
option?
yeah. Sorry, I forgot to tell you. Like as we have MSC, okay, the cost function MAE, we similarly have accuracy. Okay, accuracy is for classification. MSC and MAE are for regression. Okay, these are for classification and this is for regression. And we also have R2. R2 is basically another metric to find to check how our model is working. By default, when we do model dot score, like whenever we write model dot score, okay, and we pass in the validation or okay, either yeah, sorry, we pass in the validation set and as well as the true predictions, it basically computes the R2 score. If I check model dot score site Scikit-learn, so yeah, R2 score. So model dot score and R2 score is same. The range is minus infinity to 1. Uh, the more the score is positive, you can say your model is working better. Okay, if the score is 0, your model is like there is no change in your model, you can say there is no change in the derivatives or in the weights mainly. Okay, if the score is in negative, your model is performing worse. If the score is positive, the model is like the positive can be it in the range of like 0 to 1 in the positive, like more than 0 to 1. So if the score is around 0.89 or 1, uh, then you can say your model is performing well. So this is just another metric. Okay, like we have a lot of metrics you can see here. This is the complete list of the metric. uh, AUC curve, there are various curves also, we will see like ROC curve, AUC curve. So yes, uh, any other doubts, guys? Okay,
No, not related to this.
okay, so let's end the session.
Param,
Yeah, yeah.
when we are going to discuss the PYQ.
Okay, just a second.